I'm Johan. I'm Swedish, but I currently live and work in the UK. I'm a maintainer of various open source projects, as Ellen mentioned, and I've contributed to the Go standard library, and I run a blog writing mainly about Go and gRPC. This is my first GopherCon, and I'm very excited to be here. I'm here today to give an introduction to WebAssembly with Go. So today we will learn what WebAssembly is, how to use WebAssembly with Go, show what's possible today, and briefly look at what will be possible tomorrow. So what is WebAssembly? It's a web standard binary instruction format like x86, but developed for the web, by the World Wide Web Consortium with representatives from all 4 major browsers, and with community contribution. It grew out of the asm.js project, which proved that languages like C and C++ could be transpiled to JavaScript and run in the browser. Google developed the native client, aka NACL, but it was never implemented by any other browsers. Instead, a joint effort was started to develop something new. WebAssembly was designed to be fast to interpret, fast to execute, and of course, secure to run. So where can we use it? It's been supported in Chrome, Firefox, Safari, and Edge since late 2017, with every modern browser that matters now supporting it. A smattering of runtimes written in a variety of languages have also appeared, with Wagon and Life being the larger Go-based WebAssembly runtime projects. The prevalence of these runtimes means that WebAssembly isn't just a language for the web anymore, but runnable anywhere the runtimes can run. We might even end up with bare metal chips implementing a WebAssembly runtime. All of that is still a way off though, and today we will focus on using WebAssembly in the browser. So how can we interact with the world from WebAssembly? WebAssembly in browsers ship with a JavaScript interface to access existing browser APIs to perform tasks such as DOM manipulation, making network calls, and using WebGL, to name a few. We'll take a look at exactly how that works with Go a bit later on. Another interesting platform interface is the recently announced WebAssembly System Interface, aka WASI. Initially designed by Mozilla and Fastly, it's being standardized by a WebAssembly working group. It's designed to be used when compiling WebAssembly for running outside the browser and provides a syscall-like interface to system features like files and network sockets. It's currently still in development, but provisional support for WASI is present in Fastly's WebAssembly Runtime Lucent and Mozilla's WasnTime. So what does it have to do with Go? Let's take a step back. Gopher.js has allowed Go in the browsers since 2015. It's a tool for compiling Go to JavaScript written by Richard Musial, aka Nilans. It supports most of the standard library, and there are many community bindings for existing web technologies, such as WebSockets, local storage, and others. It's very easy to use. As this graphic shows, you simply provide your main Go file to Gopher.js build, and it spits out a JavaScript file that you can load in your HTML. It remains the most mature way of running Go in the browser, and is used by open source projects such as Parkeep. So what about WebAssembly? In early 2017, Brad Fitzpatrick opened a tracking issue for implementing a WebAssembly target in Go. The conversation quickly took off, but no real consensus was found on the best way to implement it in the existing compiler codebase. The WebAssembly spec is notably missing the goto keyword, which makes implementing control flow harder, and this hindered initial work. However, by November 2017, Richard Musial, the author of Gopher.js, announced that he had started working on implementing a WebAssembly target for the Go compiler, and it shipped in Go 1.11 roughly 9 months later. Richard deserves a lot of credit for his amazing work in bringing this novel architecture to Go on his own in his spare time. So Go 1.11 shipped with experimental WebAssembly support, which means that it doesn't have the same backward compatibility guarantees as the rest of the standard library, and this is still true today, with no clear plan on stabilization. You can expect breaking changes to still happen between releases, so be careful when considering using it for production code. It supports most of the standard library, including NetHTTP client requests, which we'll see more about later. Currently, only the JavaScript system interface is implemented, but there are plans to implement WASI in future Go releases, hopefully as early as Go 1.14, which should ship early next year. As the graphic shows, compiling Go code for WebAssembly is as easy as any other CGO-free cross-compilation. You simply specify the Go OS and the Go Arch environment variables when building. So let's briefly discuss the elephant in the room. As we'll see, it produces quite large binaries, and there's a few reasons for that. Small binary size was never a design goal of Go, and you probably yourself noticed that large Go codebases tend to produce large binaries. The CockroachDB binary is 123 megabytes large, unstripped. The heavy Go runtime, garbage collector, and difficulties of performing dead code elimination in a language that has runtime reflection all add to the problem. The image we're looking at here is the weight of each package contents in a Hello World binary built for Linux AMD 64. It adds up to 1.2 megabytes. Furthermore, we discussed earlier that WebAssembly doesn't have a goto instruction, and this leads to larger output for the same functionality. We'll discuss later what we can do about file size, though. So how can we use it with Go? So there's a little bit of server setup necessary, mostly just to set the content type correctly. Browsers will not parse and run WebAssembly files unless they have the correct content type set. The Go standard library comes with a very important file that ties your compiled WebAssembly file to the browser APIs. This is the wasm_exec.js file that marked as mandatory here. Make sure you're using the same version of this file as the version of the compiler you're using to compile the WebAssembly. This is most easily accomplished by copying from Go root when building, and I'll show an example of it doing this later. wasm_exec.html is also provided, but simply as an example of how to load the WebAssembly, and it expects a test.wasm file. I've included a little server here that serves from the file system and sets the content type appropriately for files with the .wasm file extension. But enough theory, let's take it for a spin. So I'm going to do some live demos now, and if you want to, you can grab your laptop and check out this repository, which contains all of the live demos that I'm going to be showing today. You have 5 seconds. Time's up. Okay, so we're going to start with a simple Hello World example. This is not a particularly interesting file. The only thing that you'll notice that is interesting here is the build tag. Now, for this example, the build tag isn't strictly necessary because we're not using any syscalls, but I wanted to show you what it looks like in this simple example to start with. Otherwise, so the build tag obviously then sets this file to only compile when you're compiling for the WebAssembly architecture and JavaScript OS, technically. So this is just a simple hello world, and let's build that. So as you can see here, we are running Go build with the hello world main.go. We're specifying the Go OS and the Go architecture and outputting it to a HTML directory, which is a directory that we're going to use to just serve the file system from. What we're then doing is copying using the go env go root to make sure that the binary Go version that we're using, we're copying directly from its Go root, the files wasmexec.html and wasmexec.js. Now, as I mentioned before, wasmexec.js is the only one that strictly has to be the same version as the Go compiler. Okay, let's run that. And I wanted to briefly show you the network tab when we're loading this. You can see this is a 2.44 megabyte large file, which is frankly unacceptable for something as small as what we've just shown. But we're going to take a look at file sizes later, so for the moment you can just ignore that part. And then if we open the console here, the standard output in what the WebAssembly architecture maps to the browser console. So if we press run that, we get a simple hello world. This message here is output from the wasmexec.js file, and it's not important, but the hello world here is what we printed. So that's a very simple example, not particularly interesting. I mentioned before that we have a JavaScript interface, and in order to access browsers from WebAssembly, such as manipulating the DOM, we have the syscall.js package. This is not meant to be used by all Gophers writing WebAssembly code, and should only be necessary when you're working directly with browser APIs. It's based on the interface Richard developed for Gopher.js with its own little adaptations because of the different runtime. If you use the Gopher.js interface, it will look very familiar. It supports sending callbacks to JavaScript, which is essential to use certain JavaScript browser APIs. Something important to note is that whenever you use the syscall.js interface, all the data you pass to JavaScript has to be copied, as WebAssembly and JavaScript don't yet have a way to share memory. As such, data transfer between the two domains should be minimized for greatest performance. What you see here is a simple example of a JavaScript snippet translated to the syscall.js calls. As you can see, this is basically writing JavaScript in Go. It's not so nice. We have things like stringly typed function names, and well, everything is strings, basically. But let's take a quick look at what that looks like in practice. So here we are importing the syscall.js package, and so make sure that you protect your file with build tags. As Pike says, syscalls must be protected with build tags. What we're looking at here is so the init function here, we're getting a handle on the global document, which is required to do things like creating HTML nodes and finding nodes within the HTML structure. And then in the main function, we are calling getElementById, and we're looking for an HTML node with the ID target. We are creating a new div, setting the contents of that div to hello world, and then we're appending the new div into the node that we found. So this is basically the JavaScript that we just looked at. It's a bit of a roundabout way of doing things, but it's in pure Go. Let's take a look at what that looks like in the browser, though. So again, we're doing almost exactly the same thing here. We're running Go build, we're copying the index.html and wasm.exec, but we're also doing a little sed magic at the end just to insert a target div right underneath the button that you saw in the previous example. So let's reload that. And in this case, you will notice that the generated WebAssembly is actually only 1.37 megabytes, which is still unacceptable, but the reason for the large difference here, which is almost twice or half the size, right, is that we're not importing the FUMT package anymore. And I'm not going to recommend you don't import the FUMT package because it's basically impossible if you're doing anything of consequence in Go. But it could be interesting to note that certain large packages do inflate the size of the generated code quite a lot. So if we run this, what we expect to happen is that we will have a hello world, but instead of writing to the console, we have it written straight to the document, like so. Oops. As I mentioned before, the Go standard library HTTP client can be used in WebAssembly code. This is possible thanks to a special implementation of the default transport in the standard library, which uses the browser fetch API to send requests and receive responses. So anytime you use the default transport, it will all just work. This includes methods like HTTP GET, HTTP POST, and any method calls on HTTP.default client. It maps things like the request body, headers, and even context cancellation into fetch parameters. It supports streaming response bodies and delivers data to the WebAssembly runtime as soon as it's been received. Let's take a quick look at that in action. So for this fetch demo, again, we're importing syscall.js directly. So we must specify the build tag. We are getting a handle on the global document, and then this little snippet here implements IO writer on an arbitrary HTML node by creating a new div element, setting the context type of the content that we're wishing to write, and then appending that new div element as a child to the current node, which is pretty cool, and you'll see how it works in a second. But then what we can do, now that we're implementing IO writer, is use the standard library logger on a target, on a element, a HTML node. So we're doing the same thing here, getElementById target that we saw before, where we're attaching a new node. But now instead, we've implemented an IO writer, so anything that gets written to this logger will be written directly to the as a child node of the target node that we selected up here. So if we just skip over all of that, what we're looking at here is basically pure Go, no specific WebAssembly stuff. we're using HTTP, the HTTP library to make requests and read responses. So as you can see here, we're about to make a post request to http://bin.org with some content and reading back the response and printing it to the logger. So this is a little bit more interesting. And the make here does exactly the same thing as before. We build the Go file, we copy awesome exec HTML and JS, and we're inserting that target div. And obviously, that's the div that we're then latching on the IO writer implementation to. So let's look at the size of this file. Now we are at 7.85 megabytes. As I mentioned before, FIMT increases the size of your package by about a megabyte. Net HTTP increases the size of your package by about 5 megabytes. So as I understand it, the main reason for this is that the Net HTTP doesn't have a clear separation between client and server. So when you're compiling WebAssembly and you've imported Net HTTP, you're also compiling the entire HTTP2 network stack into your WebAssembly. So it gets pretty large. But again, let's ignore that for the moment. Actually, let's keep the network tab open. What we're expecting to do here is to make a network request to HTTP bin and just print the response straight to the DOM. So I'm going to leave the network tab open so you can see this happen in case there's any network failures and I have to stand here waiting for it to finish. And, ooh, perfect. Wow, that was quick. So, as you can see, everything just worked, which is great. And we have printed the output of the log message into the DOM, which is pretty cool. And you can do this for, if you want to write like a streaming response, you can kind of stream it as it comes back. Obviously, the body that gets returned from the fetch is a reader, so you can read that asynchronously from as the response comes back. So you might think it'd be hard to run tests when it requires a WebAssembly runtime to run the code, but it's actually not so bad. A little known feature of the Go test tool is the exec flag, which allows you to specify a test runner to use when running the tests. It will automatically choose a test runner based on the architecture and OS chosen if a binary called go_os_exec exists in the path. Arch_exec exists in the path. So the Go standard library comes with a go_wasm_js_exec that can be used to run tests against a node environment, which is how the standard library tests are run. If you're anything like me, however, you refuse to install Node on your machine. Fortunately, there's a third-party package developed by Agniva Saker, which allows us to run compiled WebAssembly in a Chromium headless window directly. Let's take a look at that. So for this demo, I have chosen not to specify a build tag because this entire code here, this entire test example, is compilable for any Go platform, including WebAssembly. And so there's no we don't have to use syscall.js because we're just using HTTP library. And we're making a network request to HTTP bin. HTTP bin will return a JSON in a structured format mapping to this JSON structure here. And we can just check that the status code is correct and that we can decode successfully and that the response body's URL is the same as the URL we used to make the request. And if all of that works, which is kind of testing the implementation of HTTP bin org really, then we let the test pass. So let's just try that for Linux AMD64, which is my current platform. If we just run go test-v, that runs in 350 milliseconds, pretty impressive, making a network request and getting the response. But if we run with the Go OS JS and Go architecture wasm specified, it will run this using a test runner in my path Oh, let's see. Actually, let's run this first so you can see. When I run make install test here, it will download the wasm browser test binary. We're then moving the name of that binary into go_gs_wasm_exec. And because the gopath/bin is in my path, the go test runner will use this binary to execute the test when it's running under the JS and wasm architecture, which is how this test is able to run at all, because I don't have Node on my machine. And as you can see, it takes a little bit longer, but considering that this is spawning a little Chromium window in the background, running a network request against HTTP bin, and then shutting everything down again, this is pretty impressive. So what happens if we put all of this together? To see the real power of Go WebAssembly, let's take a look at something a little bit more interesting. Abaddon is a 2D games engine written in Go. It supports a dazzling array of platforms and is one of the premier choices for writing 2D games in Go. It's been used to write games by professional game studios. Interestingly, it supports compiling for the web, initially via Gopher.js and recently also via WebAssembly. It leverages the WebGL browser API to efficiently render frames, and this relies on the syscall.js interface we saw before. So let's take a look at one of the Abaddon demos running in WebAssembly. So what we got here, well, let me undo my changes. What we got here is a demo copied from the Abaddon repository, which you'll see it in action in a moment. But what I want to kind of impress upon you here is just how much standard library stuff and third-party stuff you can actually already do in WebAssembly. So we have font handling here. We have image manipulation, and obviously Abaddon being able to run at all is very impressive, I think. We should also hopefully have some audio in this next demo. So I'm gonna build this, and there will be a slight difference between this and the previous examples. We're still running the build using wasm and JS as the OS and architecture, but we're using a custom index.html because when you load your Abaddon demo, you don't want to have to press the run button for things to happen. You just want it to load as soon as it's ready. So let's run that. And you'll probably be curious to see how large this file is. So, okay, actually, let's take a look at it first. What we've got here is Flappy Gopher. Oh, okay. Wait, one more try. Okay, never mind. I was never very good at Flappy Gopher, or Flappy Bird for that matter, but there you go. And it's pretty cool. You can see a little FPS counter in the corner here. We're running this at 60 FPS in the browser, so you can take your everything game that you've developed for mobile or whatever, and you can compile it and just host it on WebAssembly. You can make a demo or something to run in the browser, which is really cool. Now, I wanted to show you could see how bad I was at that. What I have here, as I was digging around a little bit in the source, and this is actually, it's quite easy to read. I haven't used Abaddon myself before, but I'm going to I'm going to make some small changes to the way that the character moves just to make this easier for myself, and so I can impress you with my skills. Let's make sure we reload this. Okay. Okay. This is not part of the demo. But you can see I've actually increased the scrolling speed a little bit, which makes this much easier because now you don't have to deal with having to time perfectly between. So it's moving a little bit faster from left to right. Ooh. Yes! This is I'll just let it crash because, thank you. I'm going to waste my entire day on this otherwise. Okay, but normally when you're writing websites, what about web frameworks? You want to have like a framework to create a website, not writing games. So Victi has been around on the Go on the web scene for a while and was purpose written for creating Go web apps with Gopher.js. It was created by Steven Gutekunst and Richard Musial, and recently underwent a rewrite to make it compatible with WebAssembly. Steven is aka SlimSag, and Richard Musial, aka Nilans, of course, the author of Gopher.js and the WebAssembly port. It uses a React-like interface with structs declaring styling, functionality, and composition. It's currently under the Gopher.js GitHub org, but don't be fooled, it supports WebAssembly 100%, and it may be moved to its own org in the near future. Let's take a look at an example of a Victi application. So what we've got here is some Victi imports and a main file, sorry, a main function which simply sets the title, setting the title of the window in the browser, and then calling render body. And as you can see here, there's no kind of explicit looping or anything. We're just doing a render body, and then we have a struct. And of course, this struct then implements an interface. It embeds this Victi.core, which is essential to using a Victi with your structs. And then we're setting some initial state here. And this render function defines how this struct should be rendered in the browser. So if you're familiar with React, this might look familiar to you, where you have something like inline HTML almost, but with the power of Go, of course. So you define a body at the top level, and the body takes a variable number of elements. You can define a div, and the div can define some styling for itself, and inside the div we can define a text area, and inside that we can define some styling, and also, importantly, define some event handling. So this text area here has an event handler that on any input event, we get the current value of the text area, and we call victi.rerender on the struct itself to re-render the page. We set some initial text here, which is just the initial state that we stored in the main function. And then at the bottom here, very interestingly, we have another struct. So this is an example of the composition in action, where instead of defining lm.div explicitly, or even defining like the entire HTML tree, you can embed structs. And so this struct, of course, also implements embeds Victi.core and implements this render function to say how it should be rendered. And what this does is, every time it's being rendered, it reads the current input value and parses it using a markdown parser, the Black Friday markdown parser, into unsafe HTML. We're then doing some sanitization, and we are printing that safe HTML directly to the element. And obviously, this is then somewhere promoted when re-rendering the page view, so it kind of cascades down the tree of functions. So let's try and building that to see what it looks like. Hopefully you have an idea already just by looking at the code, but I don't, I'm not that good. So again, we're doing almost exactly the same thing. We are using this kind of minimal index.html, which loads the WebAssembly and then immediately displays it. We're not going to include a run button. Bye, Flappy Gopher. And okay, so this file is 4 megabytes, which isn't that bad considering what we've seen. But as you can see, with that simple main file, what we've got here is a really kind of interesting page, and you can see that this automatically, oh my god, I haven't prepared this text. Blah. It automatically updates things as you type it, and you can do. Oh, yep, you can. So you can see how powerful this is. Like we only had like 70 lines of code, and we got all of that functionality right in and it's like so expressive. You even have the styling, right? The putting this window over on the right-hand side, putting this part over on the left-hand side. It's all in the code there. Okay. But Victi is not the only WebAssembly Go framework. Booboo is a relatively new entrant to the Go framework scene, written by Brad Peabody. where Victi is a framework inspired by React. Vugu takes a lot of cues from the Vue JavaScript framework, as is evident by its in-markup logic and bindings. It uses a custom file format that is a superset of HTML coupled with a code generator to produce the final code that gets compiled. It's put a lot of effort into the development environment with features like automatic rebuilds and reloading on code changes. You can try it out on the online playground, but let's take a look at the quick demo. So what we've got here is a root.vugu file. The Vugu file extension is this custom file format. And as you can see, this here just looks like HTML with some extra properties here that we're not used to seeing before. And if you used Vue before, this kind of thing will look pretty familiar. But instead of interpreting JavaScript, we're interpreting Go code. So these kind of properties that you're putting inside of your ifs are Go statements. You can put kind of raw HTML strings here if you want to. You can also do a for loop, so you can iterate over like a map or an array or a slice or something like that, and draw elements based on the contents of your data. And so this what we're doing here is actually iterating over a map. So we have access to both the key and the value properties. And then at the bottom, we have a button handler. So this @click property defines what function should be called when you're pressing this button. And what this application, we'll see the demo in a minute, but what this application does is just fetches the latest bit comprises and prints it to the screen. So how does it do that? Well, we have this script type application /xgo also inline in your markup to define your Go logic for the handler. Obviously, the only entry point to this is this data.handleClick function. What we've got here is we've got some root data, which is just the global variable for this file. And then we've got a struct here, which is just a structure that maps to the JSON response for the API that we're going to use. And then we've got the handleClick function. And importantly, that you need to, when you're doing something asynchronously, like making a network request, you need to run it in a Go routine. And Vugu provides these lock functions if you want to update state from inside a Go routine. So the first thing we're doing when the button is pressed is, well, we're resetting the value, and then we're starting a Go routine and setting loading flag to true, and then unlocking the rendering. We're then making a HTTP GET request using the fetch API, as we saw demoed before, to the Coindesk API, and to just get the current price for Bitcoins. We're doing some error handling, closing the body, etc., parsing it into our struct, and then assigning this value straight to the data while holding the rendering lock. So let's take a look at what that looks like. So as I mentioned, when you're working with Vugu, you use this tool called VuguGen, and so I've kind of adapted the Vugu workflow a little bit to look similar to the rest of the demos, but VuguGen works a little bit differently from the other tools. But you can see me using it here to generate certain files from this root.vugu file. So when you're using VuguGen, you just specify the folder that your Vugu files exist in, and it will go ahead and generate a root.go file for you that you shouldn't be touching yourself, but you can see has all of these kind of magic things that you then compile to WebAssembly using the folder. So we're doing a compilation to WebAssembly here. We are again using a index.html which loads directly into the browser. And of course, awesomeexec must be the right type, right version. Oops. So let's take a look at that. Oh. Oops, that actually worked. So this one is 11 megabytes large. That's mostly, again, because we're importing the net HTTP and a few other things. Worry not. And then when we press this button, we expect to see a brief loading flag. If you remember, we set the variable to loading before we make the network request. We'll then expect the network request to come in and a response, and then printing the value to the page. And loading, and boom, nice. And ooh, almost $10,000. I hope you bought when it was down at 3,000 again. Okay, so that's Booboo. So we've seen a few demos, but what can we do about file size? All the demos we looked at are served uncompressed, but we can get a quick win by using compression. And gzip compression is usually so quick that you can do it directly in the handler. Let me show you a quick example of that while we're here, actually. If we run my wasmexec repository has a main function that takes a flag that just adds a gzip handler using the New York Times gzip handler, thank you. And if we reload the page with the gzip handler, you'll see that we're down to 2.5 megabytes from 11 megabytes, which is already a huge win, right? So if you make a hello world which is 1.4 megabytes, you get this down to about 500 kilobytes, which is still quite a lot for a hello world, but already like a huge win. Other things you can do include using a CDN for static files, which will add this kind of compression automatically, but will also ensure your files are available at data centers all over the globe, which will help latency and download speeds. The brilliant Dave Brophy put together a tool called WebAssembly and Go, which automatically builds and uploads your WebAssembly to a CDN, so feel free to try that out. We saw at the start that the standard library is somewhat responsible for the compiled file sizes, and we can in part help with that with the file size by avoiding certain imports, but let's be honest, we don't want to do that. We love Go because it's simple and it just works. So maybe there is something else. Enter TinyGo. It was created by Eike van Latem primarily for using Go on microcontrollers. It took the Go WebAssembly community by storm when the first WebAssembly demo showed that it could produce tiny outputs. It's built on the LLVM stack, and it's still very early days, but a very exciting project to keep an eye on. It recently added a garbage collector in the latest release, which makes it closer to being ready for general use. If you want to learn more about TinyGo, make sure to watch Ron Evans' talk tomorrow morning. And let's take a quick look at an example. So for the TinyGo demo, we're not going to look at any source code. We're just going to we're going to build a canvas demo created by Louis Figueiredo. And we're going to run that. This is built with the standard toolchain. So when we load this page, let's just take a look at the file size. It's 2.58 megabytes, and it does some kind of cool graphical stuff when you move your mouse around. And you can actually see the source code itself in the background here, which is kind of rad, I think. So you can see that it doesn't use any third-party packages. It uses syscall.js to draw things directly using WebGL, which is pretty cool. So thanks, Louis, for that demo. And if we instead use the TinyGo compiler, what I'm using here is the TinyGo Docker container. In case you don't want to install TinyGo yourself, you can run it using the Docker container. Again, TinyGo has its own wasmexec.js, so make sure you are copying the wasmexec.js from the TinyGo repository, or in this case, the Docker container, when you're compiling with TinyGo. And let's see what that looks like. So first of all, we reload the page. Actually, that's not going to be entirely fair. Let's just reload the page and take a look at the file size. We're down to 33.4 kilobytes. So this is like firmly within acceptable range, right? Even for a graphical demo like this, downloading 33 kilobytes is something that's not that big of a concern. And you might ask yourself, well, why is it so much different? And as I mentioned briefly before, TinyGo is built on an entirely different compiler stack from the Go standard library, the Go standard compiler, and it doesn't have the same runtime, it doesn't have the same garbage collector, everything is different. In fact, it doesn't even have a standard library implementation of NetHTTP right now. So there isn't like a lot of things you can do with TinyGo. You can do this, which is kind of cool if you're interested in like showing dots on the screen to someone. You can doing that really well. And generally, any of these kind of syscall.js only demos, which there are a few of them out there, and like doing WebGL stuff, TinyGo can do really well now, and like to the point where it's small enough. When you compress it, you get this down to like 10 kilobytes. So it's small enough that you can do some really good stuff with it. So we've seen what's possible today, and it's quite a lot already, but we have more good stuff to look forward to in the future. So I've picked out a few things that I would like to raise. We saw earlier that you can interact with browser APIs via the syscall.js bridge, but this is pretty annoying, and it basically means writing JavaScript in Go. What if we could have nice, idiomatic, type-safe APIs created for the browser APIs? This is a bigger job than you might think. Fortunately, there's a project called Go Web API, which tries to generate Go-friendly APIs from the web IDL definitions, which means we can do away with syscall.js for accessing the JavaScript world in the browser. WebIDL defines all the browser APIs, and automatically generated APIs would mean we could quickly access new APIs and easily keep up to date with changes to the existing ones. So I've shown you an example here of what working with syscall.js looks like and what working with web API generated APIs look like. So you can see that it's basically static typing, right? So it's like going from Python to Go. Among the things planned for WebAssembly itself is a proposal to make it easier to interact with browser APIs directly from WebAssembly, instead of going via the JavaScript bridge. This should mean no copying of memory between the WebAssembly and JavaScript world when using browser APIs, and not having to worry about the JavaScript callbacks and the like. Another feature on the horizon is WebAssembly threading, which is already available to testers in Chrome 70 and above. Go is very good at concurrency, and while the current implementation doesn't support Go routines, so it supports Go routines, threading is not yet supported. The last thing I've picked out is garbage collection, which is interesting to us Gophers for several reasons. What, you might say, we already have a garbage collector. But that's one of the reasons why the compiled file size is so large. If we could exclude the garbage collector when compiling Go code for WebAssembly and instead rely on the garbage collector built into the WebAssembly runtime, we might be able to produce much smaller binaries. And perhaps the most exciting thing of all, we already discussed WASI briefly, but I wanted to come back to it again because it really is worth mentioning twice. Imagine compiling an application once and distributing that binary to Linux, Mac, Windows, Android, iOS, web, anywhere you have a WebAssembly runtime. We could finally realize the promise of truly portable binaries without having to resort to using the JVM. So where does this leave us? This is one of the graphs produced by Todd Kulesa and Steve Francia based on the Go 2018 survey results. To me, this was the most interesting and surprising result of the entire survey. Let's remember for a moment that the WebAssembly support in the standard library is entirely the result of open source contributions, primarily led by Richard Musial. I'd like to think that this graph will make the Go team invest some more resources into the development of the WebAssembly targets, but also encourage you guys to bring your own ideas and contributions. The potential for WebAssembly is huge. So in conclusion, we've looked at what WebAssembly is, how we can use it with Go, what's possible today, and what will be possible tomorrow. WebAssembly itself is going to continue to evolve with new features added over time. It could not only replace JavaScript in the browser, but potentially realize the promise of truly portable system binaries. What will you build? Thank you.